So chapter 16, acid-base equilibria, acid bases, and what we call the pH scale. Some of you may be familiar with it. Some of you may not be familiar with it, but this is what we're going to take a look at. So let's do a review from Chem 1. The acids you dealt with in Chem 1 are called Arrhenius acids. Savante Arrhenius came up with this definition, and it's essentially phenomenological. If I have a beaker, let's say of some water, and I put an acid into solution, what you have is some kind of ionization that puts hydrogen ion in solution with H2O. I'm going to talk about the chemical reaction that happens between hydrogen ion and H2O, forming the hydronium ion. There'll also be some sort of an anion depending on the acid that you put in solution. So acids dissociate, they make hydrogen ions in solution. In water, hydrogen ion exists as a hydronium ion. So we could write this exact same reaction. If I put hydrogen ion in solution, here's that hydrogen ion in solution, and you have water molecules in here. And the hydrogen ions are a very reactive species. Water is a very polar molecule with a partial negative charge on the oxygen end. This is a big positive charge, and so electrons, which are negative, love the positive charge of the proton in water. That's why we call acids proton donors. They don't donate a proton to water or to whatever solution you're putting the acid into. And in any case, what you wind up getting is what we call a hydronium ion. There's a lone pair of electrons here. And so this is the species that you're going to get, and we call this a hydronium ion. And it is a more thorough description of a hydrogen ion in water. Usually this is going to be the equation that we use, or the reaction that we use to describe the dissociation of an acid in water. We'll just put the AQ there so you know that it's in water. But this is more realistic. This is the Lewis structure for this trigonal, pyramidal, tetrahedral electron geometry, trigonal pyramidal molecular geometry, sp3 hybridized oxygen for the hydronium ion. So if you include water, then you would describe this as H3O+. But just remember that when we say hydrogen ion and hydronium ion, we're simply talking about a hydrogen ion in water. Okay? An Arrhenius base forms hydroxide in solution, and we typically describe this just as, so this is sodium hydroxide. It dissociates completely. It's an ionic compound that dissociates completely into sodium cation in this case and hydroxide. This is what we focus on when we talk about a base. We're an Arrhenius base. We're talking about hydroxide ion. All right, so let's talk about neutralization reactions. Acids and bases react to form water, a non-electrolyte, and a salt. So here is your strong acid, which is HCl. So this is a strong acid, which I'll just abbreviate SA. This is a strong base. Both of these are strong electrolytes. So we might also describe them as SE, strong electrolytes. They dissociate completely, and they form the non-electrolyte water. And the non-electrolyte water is the driving force for this acid-base neutralization reaction. The other product of this is a salt, and this is just a set of spectator ions in this strong acid, strong base reaction. So the net ionic equation for this strong acid, strong base reaction is just H plus OH minus makes water. This is going to be the nuts and the bolts of your acid-base neutralization, the hydrogen ion, the proton representing the acid component, and the base component, the hydroxide ion in this Arrhenius definition. They combine to form the low energy product water, the non-electrolyte. So that's the net ionic equation. Sodium and chloride are just spectator ions. So thus far, we have stayed within the context of the Arrhenius definition, and I want to remind you that the Arrhenius definition of an acid and a base always involves water, H2O. So if you're trying to distinguish an Arrhenius acid-base reaction from, let's say, a Bronsted-Lowry acid-base reaction, and later on I'll introduce a Lewis acid-base reaction, just remember that the Arrhenius acid-base reaction always involves water, but the Bronsted-Lowry acid-base reaction doesn't have to. It can. You can have, in fact, a Bronsted-Lowry acid-base reaction, which involves donating a proton and the acceptance of a proton for the base. That's what the base does. It accepts the proton. The Arrhenius definition satisfies that completely, but not all Bronsted-Lowry acid-base reactions involve water, and we're going to deal with that. All they look at is proton transfer. The donation of a proton, that would be your Bronsted-Lowry acid and a proton acceptor, which does not require hydroxide ion, but could. All right, so let's talk about conjugate acid-base pairs. So here is hydrofluoric acid. It's a weak acid. We're going to put it into water. What's going to happen is we're going to call, I think you would recognize this as an acid, and it's going to donate this proton to water, and the result of that donation is the hydronium ion. So in a sense, we can look at water as the base, because it is, in the Bronsted-Lowry sense, because it's accepting the proton from the acid. Now over here on the product side, we have the anion from the acid, and the anion of the acid is what we call the conjugate base. When HF is donating a proton that is behaving as an acid. And on the other side, on the product side, in this particular case, we have a hydronium ion. And the hydronium ion is acting as the conjugate acid when water is acting as a base. So you'll notice that conjugate acid hydronium ion and water, they have H2O in common. The conjugate acid simply has one more proton, and that's always going to be the case with Bronsted-Lowry acid-base reactions, okay? And the conjugate base on the opposite side of the reaction is going to have one less proton. So this has one less proton. So you can always recognize their conjugates. Conjugate bases have one less proton, conjugate acids have one more proton, and they have the anion in common. Okay? All right, so HF is the proton donor, water is the hydrogen ion acceptor. Hydrogen ion is our proton, because remember, take an electron away from hydrogen atom, and all you have left is the proton. There are no neutrons in the nucleus of normal hydrogen. So in this case, if I reversed the reaction, now what's going to happen? Well, the hydronium ion is going to behave as the acid. And what's that mean? Well, that means it's going to donate a proton to fluoride ion, which is going to accept the proton. So that means that fluoride ion is behaving as the base. Over here on the opposite side of the reaction, we've got the conjugate acid when fluoride ion is behaving as a base. Remember that the conjugate acid on the opposite side of the arrow will have one more proton, which HF does. And then we have the conjugate base, which is water in this particular case, because water has one less proton than the hydronium ion. All right, so try and get that squared away. We'll do a little practice here in just a bit. Hydronium ion is the proton donor, fluoride ion is the proton acceptor. Conjugate acid-base pairs. So here we have the acid, HF, the base, water. It's going to accept the proton from the acid, and the conjugate base, which has one less proton on the product side over here than the acid did on the reactant side, and the conjugate acid, which had one more proton than the base did when water's behaving as a base. Okay, so there you go. Fluoride ion is the conjugate base. When HF is acting as an acid, hydronium ion is the conjugate acid of water when water is acting as a base. So really, the conjugate acid-base pairs are about the behavior, the acid-base behavior that you have. So each acid has a conjugate base on the other side, each base has a conjugate acid on the other side. And it really doesn't matter whether we put the, say, conjugate acid or conjugate base on the product side or the reactant side. Each acid has a conjugate base and each base has a conjugate acid on the other side of the reaction. So let's identify the acid and the base, the conjugate acid and the conjugate base. This is formic acid. That is the acid that ants inject into you when ants are stinging ants like fire ants. And cyanide, you can recognize that cyanide has no proton, so it can't be the acid because acids in the Bronsted-Lowry context have to donate a proton. So this is going to be the base. Over here, we're going to have the conjugate base when formic acid is behaving as an acid, and the conjugate acid when cyanide is accepting a proton and acting as a base. And that's the way we identify them. Here we have sulfite ion. It obviously has to be the base because it has no protons. This is hydrogen phosphate. It's going to donate a proton, so it must be the acid. And then we have hydrogen sulfide or bisulfite, which is the conjugate acid when sulfite's behaving as a base, and phosphate is the conjugate base when hydrogen phosphate is acting as an acid. Okay? And then finally, we've got bicarbonate down here, hydrogen carbonate, which is going to behave as the base. Now, this might be confusing because you go, well, it's got a hydrogen ion, but if we look at the product side, it's gained a proton. So it's actually at the base in this reaction, and water is going to behave as the acid because you look over here on the product side, you've got hydroxide ion. So water is donating the proton to bicarbonate. So carbonic acid is the conjugate acid and hydroxide is the conjugate base. So don't be fooled. Just look who's donating the proton. That's the acid. Who is accepting the proton? That's going to be the base. All right? So trends in conjugate acid-base pairs. Conjugate acid-base pairs contain the same anion. Only hydrogen ion is exchanged. The conjugate acid of a substance always has one additional proton in the formula. The charge becomes more positive. The conjugate base always has one fewer proton in the formula. The charge becomes more negative. So here is the clicker question, and I'd ask you to identify the conjugate base of the ammonium ion. So how would I analyze this? Well, who's donating the proton over here? We're looking for the conjugate base of the ammonium cation. So remember, the conjugate base will have one fewer proton. The conjugate base and the acid will have the anion, or the, in this case, it's not necessarily an anion. But I'll let you go ahead and answer that question in class. Here's another one. Identify the conjugate base of the bicarbonate ion. So this is an ion, but it can still act as an acid. And acids do what? They donate protons in the Bronsted-Lowry sense. They're donating protons, and so you're looking for the conjugate base of the bicarbonate ion. Now remember, conjugates can be on either side of the reaction arrows. You're not necessarily pinning conjugates on the product side or the reactant side. They can be on either side. Every acid will have a conjugate base. Every base will have a conjugate acid on one side or the other. And I think this is the last one. Here we've got HCl, a strong acid, and water. And I'll let you answer that on your own. I think I've talked enough.